But if somebody's absent, they can refer to it later. Any questions? Are we all good about all what's going on here? So, let's just work through what we've done so far on the project, and then we'll move forward from there. We'll also review some of the major ideas, some of the main things I want you to have in your brain and that you'll know for when we get to test time. Oh, I see what's going on. It didn't open on the screen properly. That's what's going on. Okay, so hopefully everybody successfully completed page 1 here. Did you do that? How many points is it worth? It's worth 1 point to include your name on there. It's also worth a point to include your name as part of the file name. So I think I uploaded it as Unit 5 Lite. You should make it be Unit 5 Lite and then your name, right? When you save it. Then on page 2, this one was just a little exercise in creating your own abstract art just by starting off with an arrangement of dots, 11 dots connected by lines, huh? Just kind of a warm up to think about and compare that to the wave diagram on the front. So that's not a big deal, but hopefully you did it because it's worth some points. And then we get into an actual lab that goes several pages where I filmed myself doing the lab with the Slinky in my garage, right? Making waves with the Slinky, and we analyzed and we measured and we compared, we counted, right? We did all those things. So with that, if you weren't here, I'm going to ask you to refer to the videos that I made during class that walk us through that. And of course, on anytime you're looking at one of my videos, if you've already got something figured out or already got something done, you can just jump up to the next part, huh? Right? Move the video to where you need it to be. And that lab went several pages, huh? And it included a diagram here that I want to go over once I get the screen back. It looks like it's doing it correctly now. So, no, it didn't do it correctly. Come on, dude. I hate arguing with technology during class. It's like, come on, cooperate. That's what I think it's auto image. Because if this doesn't fill the screen, then I can't write on it in the right place. So there we go. That looks better. Let's see if it's going to work for me. Yes. Okay. So I want to draw your attention to these diagrams right here. This is page 5. Okay. Just these diagrams with the arrows. So the arrows, the long arrow, is showing that there's a wave moving from left to right. Like if you were at the lake, the beach would be over here, huh? The wave is coming in towards you. But the disturbance that created the wave either went perpendicular to the direction the wave is moving, it went across the wave, in other words, or the disturbance went in the same direction as the wave. And I'm thinking about this now that I'm looking at it, and I'm kind of asking myself, why didn't I make this a double-headed arrow? Maybe that would have made more sense if it was a double arrow instead of a single arrow, because this wave disturbance is actually going up and down here, right? And this wave disturbance is actually going back and forth here. So maybe that would make more sense if it was a double-headed arrow. But what I want to ask you is which of these two disturbances would create what we usually think of as a wave that would look like this, and which one would create the other type of wave, which we show like this. We have a bunch of material squeezed together, then it's stretched apart, then it's squeezed together again, then it's stretched apart, squeezed together again. Which one would be, let's call this A and B. Which would this be? Excellent. Both of you, excellent. So, oh, I'm sorry, what happened? So this wave that we usually think of as a wave is A, isn't it? Dang it, stop that, you. It's just acting up here and not doing what I want it to do. Putting everything in boxes. I don't want those boxes. So this would be wave A over here. This would be wave B, correct? Yeah. This wave that we usually think of as a wave going along like this is formed by a perpendicular disturbance. Whereas the other wave is formed by a parallel disturbance, moving back and forth in the same direction. So the wave's coming along like this, isn't it? Whereas this wave, what we usually think of going up and down as the wave is moving forward. Yeah? Okay, names. Which one is which? Do you guys agree with Quetzali? Maybe you didn't hear her. She said transverse was A, longitudinal was B. What do you think? I think transverse means across something. Does that look like what's happening with the disturbance is moving across the wave for A? And longitudinal means the length of something along the same direction as something. And does that look like what's happening with B? That's absolutely correct. Good job. So here we have transverse. And here we have longitudinal. Yeah? Final question. Which of these is a sound wave and which of these is a light wave? A or B? B is a sound wave, correct. A is light. Yeah? Yeah, light wave moves like this. Although didn't we talk yesterday about how it's actually a double wave, electro and magnetic at the same time? Did I try to do this? It's kind of tricky. So A, the light wave, is a transverse wave. The disturbance that created it is in the opposite direction as the wave itself is moving. B, a longitudinal wave, like what we have in sound, the disturbance that creates it is moving back and forth in the same direction as the wave is moving. Like right now, when I'm vibrating my voice box, that's pushing the air molecules together, squeezing them together, and then pulling them apart every time my voice box vibrates, So we have this squeezed area and this stretched out area. Now let's go to these waves and can we label their parts? What would you label this? What would you label this? Over here, what would you label that? What would you label this squeezed in part here? I can draw a proper bracket. So I'm going to go 1, 2, 3, and 4. What's part 1 over there? That's the crest or the peak. Either the crest or the peak. And number 2 is the trough, like the trough where a horse would drink water, right? Kind of like I guess you could think of it like a ditch. Yeah? The crest or the peak, same thing. and then the trough. What about 3 and 4? Very good. Good. The zones of rarefaction, where the molecules are spread apart. They're rare. We say they are rarefied. There's fewer of them. They're stretched out. And then the zone of compression, where they're squeezed together. Yeah? Let me see if I can do this. Let's take this down just a little bit. Oh, this is good. This will work. Okay, let's move on to the next page. If I measure from top to bottom of this wave versus measuring from peak to peak of this wave, what are those two different measurements? Yeah, Armando.
Measuring the length of the wave up and down.
This one?
No.
This one. The height of the wave. Good. This is the amplitude, how tall the wave is, huh? Not quite frequency. The distance from one peak to another is isn't that a length? It is lambda, right? Lambda is the Greek letter L, which represents length, which in this case is the wavelength. Distance between one peak and another, I'm going to label it as lambda, right? Now, frequency, that's when you count how many waves have gone by over 1 second, huh? So let's say it took 1 second for this to go by. What would the frequency be? That would be 5 waves per second, huh? That would be the frequency. Okay? So we've got amplitude, we've got wavelength, and we've got the trough and the crest and the peak. Now, what if we compare this to our longitudinal wave? Do we still have these same measurements of wavelength and amplitude and frequency with this other type of wave? Do these exist? Absolutely, and they're quite similar. So, for example, the height of the wave, the tallness of those waves would be the amplitude, and the distance from one zone of compression to the next zone of compression would be the wavelength. So the zone of compression is kind of similar to the peaks, huh? You could think of it that way. So this is now lambda over here. Hey, look at my diagrams. Which one has a bigger wavelength? The light wave or the sound wave? Bigger wavelength. In other words, lambda is longer, huh? Right? So the sound wave has the bigger lambda, the bigger wavelength here, doesn't it? Which one has a bigger frequency? Yeah, if we look at this, it has 5 peaks, huh? How many zones of compression did I draw? Only 3. So this one has a smaller frequency. This one has a higher frequency, huh? Is that okay to make those comparisons? So tell me this, if this is lower frequency but longer wavelength, what do we call that relationship? The wavelength got bigger, but the frequency got smaller. If one goes down when the other goes up, we call it a inverse relationship, right? Now tell me this, what did I change here on this wave? I changed the amplitude. For light, that would make it brighter. But it wouldn't change the color of the light unless I change the wavelength too. And the same thing is true for sound. If I made these sound waves taller, then how would we experience that sound? It would be louder, yeah. But if I squeezed the zones of compression together, it wouldn't change the volume, but it would change the pitch. Right? To change pitch of a sound, you change the frequency. To change the color of light, you change the frequency. Are we good with that? Okay. So that was a pretty big review. Let's see where that takes us. We've already done that. Oh, we compared these guys. Can you see that they have different wavelengths? And that means they have different frequencies, huh? Which has the longest wavelength? The top one, the middle one, or the bottom one? Top one has the longest wavelength. Which one has the highest frequency? The bottom one, huh? Short wavelength, high frequency. They go the opposite way. They're inverse, aren't they? Nice. And then we did this little graph comparing wavelength and frequency. And if the inverse relationship is true, your graph should basically look like that. Yeah? Does it drop down with a negative slope, showing that inverse relationship? Where am I at? I'm on page 8 now. So we've already done that. Page 9. This is actually the first thing we did, because on the first day of class this semester, I needed to show people how to do these PDFs. And so I just asked you to work on this on your own, huh? Yeah. You read and answered questions from a website. You did a review quiz. You took notes from a video. If you haven't done any of this, can you still do it on your own time? Yeah, but we're not going to take class time to do it. Page 10, I asked you to do this on your own. You were supposed to read and answer questions. But did you also highlight while you were reading? Highlight the important text? That's worth some points, that highlighting, okay? Page 11, I asked you to do this on your own. Answer these questions basically by analyzing the graph. Now I want to point out something about this graph that I do like and something that I don't like. I do like that they showed the different wavelengths of the different kinds of light, but I don't like that they kind of merged them together. When I look at this, it seems like the wave is getting faster and faster, but that's not true. It's actually just showing all these waves, and they should be separated from one another. Every wave is actually separate from the others. It's not like they're interconnected. You okay with that? So which has the longest wave of all those types of energy? Radio, huh? Radio and TV. And which has the highest frequency? Gamma. Which one has the lowest energy? Radio. Yeah, because if it's higher frequency, it's higher energy too, huh? Is that direct or inverse relationship? That is direct relationship, yeah. When frequency goes up, energy also goes up, huh? And doesn't that tell you that radio waves are pretty safe to be around? But gamma rays are too energetic for us. Not very safe. In fact, radioactive materials release gamma rays. Exploding stars release gamma rays. You don't want to be near that. Radio waves, though, they just either go right around us or right through us, and it doesn't even matter. So you're supposedly already done with this page too, huh? Something you can do on your own if you haven't caught up with us. And here's that diagram again. Didn't we look at this briefly yesterday? Where it shows the electric field going up and down, and it shows the magnetic field going back and forth simultaneously at the same frequency with the same wavelength. Can you see that? It looks like the magnetic field comes towards us in purple at the same time that the electric field goes down in red, huh? And they're perfectly in mesh with one another, aren't they? Oops. Something like that. All right. Then we looked at the electromagnetic spectrum as a whole, didn't we? And I wanted you to do this on your own. And maybe you've fallen behind on this, which means you have the dreaded homework to deal with. And let's see. Let's review this. First of all, can you list the different colors of visible light, of the visible spectrum? Can you list them in order? From lowest to highest energy. Oh, you left out one. The one we don't even think of as a color usually, huh? Yeah. Yeah, where does indigo belong? And what's the guy's name that helps us remember this? Roy G. Biv, right? So if I ask you to list the different wavelengths of visible light in order, that's in order. Roy G. Biv. But the question is it in order from low energy to high, or is it from high energy to low? Which has more energy, red or violet? Let's look at the waves. Red looks like this. Oops. Red looks like this. Violet looks like this. Which has more energy? Violet has more energy, which means its wavelength is shorter and its frequency is higher. You okay with that? Now let's move to the entire electromagnetic spectrum. Can you list the 7 kinds of light in order from the electromagnetic spectrum? I gave you a reminder yesterday that visible light is where, on that list of 7, where is visible light? Exactly in the middle. And how many have less energy than visible? 3. How many have more energy than visible? 3. Okay? So on this diagram, it's kind of hard to see here. Can you see we have them here in blue? Radio, microwave, infrared, visible, ultraviolet, X-ray, gamma. Which one's the high energy? Which is the low energy? Yeah, gamma's high energy. Oops. Gamma's high and radio is low. Yeah? There's 3 on each side, huh? And where does Roy G. Biv fit into this? Well, it's all squeezed right in here in the visible, isn't it? Does that make sense? If we can see it, can you see red? Can you see orange, yellow, green, blue, indigo, violet? Can you see all those? Yes. And notice what's right next to red. Right next to red is infrared. Infra means below the red. Its energy is a little less than red light. Now, I noticed when you turned in your light math yesterday, a lot of people made a mistake on this. I asked you which type of light has a wavelength slightly longer than 800, and a lot of people said red. But that's still visible light. I wanted longer than visible light, which is infrared. Similarly, I asked the question, which type of light has a wavelength shorter than 400? The 400 was violet, but what is slightly shorter than that? What's just past violet? Ultraviolet, which means beyond the violet. Okay? So if you see that you missed questions that you said red and you said violet on the light math assignment, it's because I was looking for infrared and ultraviolet, which are types of light we can't see because they're beyond the visual spectrum, the visible spectrum. Andres, did you have a question? Longer than 800, lower energy than 800 is infrared. Shorter than 400, in other words, higher energy than 400, because the shorter the waves, the more energy it has, right? As opposed to the long waves, would be ultraviolet. And what's past ultraviolet? X-ray. What's past X-ray? Gamma. Right? So I would like you to memorize not only Roy G. Biv, but this list of the different types of light in order also. Let's see. If we take each of their letters, what do we get? Radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma ray. Could we put something together like Roy G. Biv to help us remember that? It's a little more difficult, isn't it? Armivux G. You could do that, or you could make a sentence. Have you ever done that before to memorize something? Take the first letter of it, each thing, and then create a sentence out of it. Radioactive mice inside violet underwear. Uh, now, do you have a visual of that in your mind? Of radioactive mice inside violet underwear? Yeah, you can create a picture in your head with that, can't you? Although we need to add X and G on there, right? I guess the X is it's censored because it's in the underwear. And the G is what you would say if that was happening. Good God or something. But if this is a great way to memorize things, and you don't have to wait for your teacher to give you a sentence to memorize, right? You create your own sentences. And if it's something that gives you a picture in your mind, it's going to work even better. Okay? So, I don't know. I just kind of came up with that halfway today, halfway yesterday. I don't know what to say. Maybe it would work for you. Maybe it wouldn't. There's different ways to memorize things, huh? Another way to think about it is visible is in the middle, and then there's 3 lower energy and 3 higher energy. Because then you only have to memorize 3. Although you have to memorize it twice, huh? 3 different ones. 2 different ones of 3 things each. Does that make sense? I do want you to know this electromagnetic spectrum, though. Okay? So practice that. Can you name the 7 colors, the 7 types of light in order? And I don't really care if it's most to least energy or least to most, but you should know which has the most and which has the least. Okay? Do we spray gamma rays around to use our cell phones? Or do our cell phones spread radio waves around? Because radio waves are harmless to us, aren't they? But gamma rays would be harmful. So if you think about that, what's harmful is the high energy, huh? Yeah.
What's that will do like?
I don't know very much about it. I wish I could answer your question. I know that there are some like rumors about the harms of cell phones and stuff. There is some potential that by having a cell phone close to our body all the time and being exposed to radio waves like that all the time could build up. I don't know if there's any evidence for it though, but some people have that concern. Um, and with 5G, I don't know anything about that. So I can't answer your question. My guess is 5G is a different frequency that allows more information to move through faster. Um, but that doesn't necessarily mean that it's going to be dangerous to us or not. I really don't know. I haven't studied it. I hate to just talk about things that I hear or see on Facebook, right? Because a lot of stuff on Facebook, it's not like those people are experts, right? Like when it comes to a mask and the decisions I make about wearing a mask, I would rather listen to an expert than somebody on Facebook who just read an article or two. Dr. Fauci has spent his entire career, decades, studying infectious disease. I think he knows a thing or two. As opposed to, oh, my friend on Facebook said, you know what I mean? We kind of have to look at our different sources of information and choose what value they have, what validity they have. Now, your friend on Facebook posts an article about the dangers of 5G, and so you look into that. Okay, but should you stop with that one article, or should you then start asking around or looking around for an expert's viewpoint? See what I'm saying? Yeah, it's fine to get alerted to a potential problem through social media. But then your final decision should really rely on expert analysis, I think, right? And when those guys have spent their entire careers working on those things. I think they know something. It's not like, oh, people just started studying infectious disease last year because that's when the lockdown hit. Is that the same as getting a doctorate, getting a PhD in infectious disease, and then working in it for decades? It's nothing like the same. So choose your sources of information carefully. Okay. Let's see. Then you had, then I asked you to do this on your own, didn't I? I asked you to do that yesterday. So this is something, once again, I'm going to want you to highlight and answer questions as you go. I would draw your attention to the diagram here. Anybody know what that object is called? That they've shown it like a pyramid, and it's taking white light and splitting it into the different wavelengths. What is it called?
Prism?
A prism. In fact, here's a prism right here. This is not a great prism for a couple reasons. One, it's plastic instead of glass. And two, the angle, I don't know if you can see that, the angle should be 60 degrees, but it's actually 90 degrees. So this one doesn't work that well, but it kind of works. So let's check it out. The best way to do this is if Andres turns off the lights here. And you guys at home, if you look at the picture of me and the screen, I'm going to try to show the spectrum of visible light up above the screen. So I'm going to use this as my light source. Would you agree that it's white light? Yeah. Okay, so white light is a combination of all the different colors. So let's see if I can create a spectrum up there on the gray part. Now that's not a spectrum, is it? That's just kind of reflecting the light. But if I twist this more, look, do you see a spectrum now? It's not very bright, because like I said, this isn't a great prism, but can you see the red, orange, yellow, green, blue, indigo, violet? It actually repeats a couple of times. Yeah? So that's a prism, which is making a spectrum for us by splitting the white light. Okay? We can also do that with another device called a diffraction grating. So here's what's happening. For both of them, you can see it in the diagram. The white light comes in at one angle, and when it comes out, the light has been bent, huh? And it turns out that the amount of bending of the light depends on the wavelength and frequency. So as you can see, the purple light has been bent towards us more than the red light. And that's why the white light separates out into the whole spectrum. Because here comes the white light, it goes through the prism and it gets bent, but which one got bent more? My left hand, my top hand, or my bottom hand? Yeah, the bottom one got bent more. This is what happens with a rainbow, is the light is getting bent by different amounts depending on the color. Here's the other cool thing about a rainbow. If you're like, oh, it's sunny, but it's raining, where's the rainbow? You always have to look with the sun at your back. If you want to find a rainbow, if you think there should be one because it's sunny and raining, you got to put the sun at your back. And that's how you look for the rainbow. It will always be, you will be between the sun and the rainbow itself. Something to think about. So the other way to split the light, besides a prism or raindrops, is with this thing we call a diffraction grating, which could either be made out of glass or plastic. And it's, imagine a graph of plastic. So take the graph paper that we have, and every little box is a bump. Can you visualize that in your mind? It's a plastic piece of graph paper, but every little box is a bump. Yeah? Now, all those bumps bend the light different amounts. The violet light gets bent more than the red light, for example, and that separates the different colors. And so the diffraction grating allows us to see these different colors. And inside this thing is a diffraction grating. So I can look through here and I can see two things. When I look at a light source, I can see the amount of light and I can see a rainbow. Very nice visible spectrum. All right? So take one. And you can look at your computer screen. You can look at the screen at the front of the room. And you can see that the white light is being split into the visible spectrum by this diffraction grating. So look through the narrow end. And you should be able to see, when you look in different directions, you should be able to see a rainbow kind of appear and disappear, depending on what light you're looking at. So you look through the little hole in the narrow end, and then you have to point it at a light source. And you should see a rainbow, and look away from the light source, it'll disappear. And it's very intense color, isn't it? Yeah. Andres, will you turn on the lights again? Let's try it with just the room lights on. Is that better? Oh, I think that's pretty good. I see a pretty intense little visible spectrum, or rainbow, huh? So as we're talking about the visible spectrum, the other thing I want to point out in this diagram that I like is not only does it show all the colors, but it shows their wavelength and frequency here, doesn't it? All the waves are given. And you can tell just at a glance that red has a bigger wavelength, a lower frequency, and that means it has a lower energy than orange. But that's less than yellow, which is less than green, which is all the way up to violet, which has the highest frequency, the shortest wavelength, and it must be the most energy too, huh? Yeah? Does that make sense, what this diagram is showing with the different light waves? Cool. Well, I want you to finish this by yourself. And so we're going to move on to page 14 together. Because I think page 13 is pretty easy to do on your own. 14 is a little tricky. Okay? So we're going to do this together. And what we're going to do is talk about light, or any wave, it could be sound also, when it goes from one material to another material. And we call that the medium. So the material that the wave is moving through is called the medium. So when light goes through air, air is the medium. When it goes through water, the water is the medium. And when we're talking about more than one medium, we don't say mediums. That's not correct. We say media. That would be the plural. Okay? Like social media, kind of, except in this case, it's the same word, but in this case, it's meaning a material that the wave is passing through. So what happens when light goes through different media? Like when the light goes from the air to this plastic prism, what happens to those light waves? That's what we're talking about, huh? Or here's another example. Imagine back in the day when you were a little kid and you went down to the lake and you put a stick in the water. And you're looking at that stick, right? Here's the water. Here's the stick. And you're going, Mom, the stick is bent. Right? Doesn't it look like the stick is bent to your eye? But is it in fact bent? No, it's not bent. What was bent? Not the water, but how does that image get to your eye? Light waves. So what actually got bent? The light waves got bent. What happens here, the light wave is just going to go straight to your eye. Here, it's going to come up, hit the water, and then get bent and go to your eye. Does that make sense? When the light moved from the water medium to the air medium, it got bent because the waves travel a little different through those materials. Right? and it gives us this optical illusion that looks like the stick is bent when it's not. Does that make sense? So that's kind of what we're talking about here. But of course, we're going to make it all scientific, and we're going to analyze it, and we're going to do some calculations about it. So we have to remember that, what is our number one equation for this unit? Velocity is equal to wavelength times frequency, right? The speed of light is equal to the frequency of it times its wavelength. Is that the same as this right here? Is this the equation in words, but this the equation in symbols? Aren't they the same? V equals F lambda, right? So according to the wave equation, wave speed, frequency, and wavelength are all related. Velocity, the speed, the frequency, how fast it vibrates, and the distance between waves, the wavelength, those are all connected. As waves travel from one medium to another, the wave speed changes. But because waves can't bunch up or accumulate as they travel from one medium to another, the frequency has to stay the same, and the wavelength must change. So keep that in mind as we move forward on this. When the wave moves from one material to another, when it crosses media, frequency stays the same number of vibrations per second. But that forces the wavelength to either spread out or squeeze together. Okay? As it travels through different media. So let's look at these diagrams. First of all, what a wave doesn't do. Notice, here's the wave moving along, and it hits this material, and crosses through it. But the wave does not bunch up at the what we would call the interface, the boundary layer between the two. What's the interface between, oh, let's look at this new poster I put up. My wife took this in Thailand when we went there one time. What's the interface between this pond and the atmosphere? Just the surface of the pond is the interface, the top of the pond. Okay? So the interface is just where one medium meets another. Between water and air, it's just the surface of the lake, the surface of the ocean. Okay? Between this and the air, it would be the edge of the prism would be the interface. Right? But look, this is what waves don't do. So don't imagine that. They don't bunch up there. They don't cluster up. But what they do is they spread out, or they could squeeze together. If this was moving the other direction, if it was moving from right to left, they're squeezing together when it changes media, So the frequency stays the same, but the wavelength will either stretch out or squeeze together. Okay? So again, we're talking about waves moving from one material to another. If the frequency didn't stay the same, I'm here now, waves would have to bunch up or become gapped at an interface where the wave changes velocity. Waves don't do that. If they did, the wave equation wouldn't work, and we'd be having a very different conversation. Instead, as soon as a wave hits an interface, the wavelength immediately lengthens or shortens, depending on the medium, and the frequency remains unchanged. So when the wave goes from air to water, the wavelength changes, the frequency stays the same. Complete the data table below for a sound wave traveling from medium 1 to medium 2. So we're going to talk about sound wave. Go back to sound waves here, okay? It's the same thing for both sound waves and light waves. So using the wave equation and your knowledge that frequency stays the same for a wave moving from medium 1 to medium 2, complete the table. Now let's look at this table. It's a little tricky. Do you see it's light gray over here? This is our first medium. It's like the air that the light waves are moving through the room. The second medium was the prism, and that's over here. So it's kind of a two-part table, and what's happening is that the wave is going from the first thing to the second thing, and it changes as a result. And we're going to analyze and calculate those changes. So here in the list of medium one, these are the materials that the wave is traveling through. So we have sound waves going through hydrogen, through seawater, through marble, through air, through human tissue. But remember, we're going from the left side of the chart to the right side. So in the first one, we have sound going from hydrogen to lead. And the sound wave is going through that hydrogen gas, and then it's carried on through the lead. Can you imagine that? Sound wave is moving from hydrogen gas into lead, into metal. Now, notice it's given us the velocity every time, hasn't it? Every time it gives us the velocity because different materials, different media allow these waves to travel at different speeds. So it's giving you the velocity. And then on the first side, it gives you the frequency. On the second, it doesn't. So we have to think about that a little bit. Get rid of some of this writing I did. There we go. Now let's look at the first row because it's already completed for us. What do we see? In hydrogen, the velocity is 1290. The frequency is 250. The wavelength is 5.16. Hey, everybody get out your calculator. You can use your phone. What was the wave equation? Velocity equals, okay, so frequency 250 times lambda wavelength 5.16. Please multiply 250 times 5.16. What do you get? 1,290. Hey, look right here. What's the velocity of sound through hydrogen? Did it work? Yeah. Double check it on lead over here. Multiply frequency times wavelength to see if you get that speed. Frequency times wavelength. Do you get, for lead, 250 times 7.84 should give you 1960, 1960. Is that true? Now, I want you to do it backwards. Because remember, V equals F lambda, right? I want you to find lambda. How do we isolate lambda using algebra? Both sides have to get divided by frequency. This just becomes 1, so our new version of the equation, it's the same equation, is V velocity equals velocity divided by frequency gives wavelength. Please test that out. 1960 divided by 250. Go ahead, pop that in your calculator. 1,960 divided by 250. Does it give you this answer? 7.84. Yeah? Okay. So this is what we're going to be doing to fill this in. Can you find the wavelength of sound in seawater by doing that same thing we just did? The wavelength of sound in seawater. How do we find lambda? I want you to work on getting this one right now. What do? Velocity divided by frequency. Okay, so you can fill in that table. What did we do? 1,540 divided by 125. Did you get 12.32? That's what you're gonna fill in here, huh? Now I have a double decimal point, just what I need. There we go, better. Okay, now, as that sound wave goes from the seawater into solid marble, it sped up, didn't it? Can you see that? It was 1,540 in seawater, and then when it hit the marble, it sped up to 3,810. But when it went from the seawater to the marble, did the frequency change or not? Remember, frequency stays the same. So what are you going to fill in here for frequency? Yeah, whatever the frequency was on the left, it should match on the right. Whatever the frequency is on the left stays the same on the right, but that means wavelength changes. So you have to do your division again to find the new wavelength. 3,810 divided by 125 gives your new wavelength. And see if you agree with me. Oops, not 48, not 84. Did it backwards. 30.48, huh? Yeah? Any questions? So there's 3 more rows for you to fill out by yourself. We have to divide to get this lambda. Then you just copy the frequency over here, and you divide to get the new lambda. So you got to do some division, but then the frequency column should be easy. You just copy from left to right. So go ahead and take a minute to fill in that chart. And then there's some questions at the bottom to answer about it. Yes. For both of these columns, you have to divide. Here's your equation you want to use. V divided by F. Velocity divided by frequency will give this. Whatever the frequency is on the left, you just copy it on the right. You have to divide to find lambda. Hey, you guys at home, give me a thumbs up when you finish this chart. Yeah. Yeah, this is a good time. You ever seen those glasses that make everything look like a rainbow? That would be a diffraction grating, just like this.
That's a question for air being practiced.
Yes, yeah. Divided by 100, 3,800, yeah. Oh, wait, I wasn't looking at the right one, actually. Which one did you get?
Air. 331.
We get less than one?
350.
I would agree.
Yeah.
Yeah. These three look right, because I've done that in my, this one. I think the other ones look like they're probably right. There's nothing that's jumping out at me from this being wrong. Finished? Good job. How we doing out there? I saw some people are already done. Anybody else have a thumbs up for me at home? Thanks, David. I already saw Allie. Thank you. All right, Angie, good job. Michelle, way to go. Okay, now we're going to start looking at these questions. First question, which medium transfers sound the slowest and the fastest? And all you have to do is look at the speed in the velocity column, right? So here's the velocity. Which one is the fastest and the slowest? But use both possibilities, correct? We've got hydrogen, seawater, marble, air, human tissue, lead, marble, air, and seawater again, and steel. So we do have two different ones to compare over there, lead and steel, along with these five on the left. Which one's the fastest and which one's the slowest? You just read it off the chart, huh? Next, the density of a material describes how heavy it is for its size, which we can also think about as being how closely its atoms are packed together. So let's think about this. Here's a basketball, right? I want you to imagine, in fact, I would like you all to send me a golden basketball. Please, next class, everybody bring me a solid gold basketball. All right, that might be enough for me to retire on, so at that point I can just give you an A. How heavy would that solid gold basketball be? Even though it's the same size as this one, how heavy is it? It's way heavier. I might not even be able to carry it, right? It has a much higher density. It's heavier even though it's the same size. That's density. Now imagine the same thing, but this is a solid wood basketball. Same size, solid wood. How heavy would it be? Probably heavier than this because it's mostly hollow and filled with air, right? But compared to the gold, if I had two basketballs, one solid wood, one solid gold, which one's heavier? Gold is much heavier even though they're the same size because gold has a higher density. Which one, what would happen if I threw those two basketballs into the lake? The wood one would float and the gold one would sink and you'd go swimming after it, huh? Right? Well, it'd be pretty hard to bring up out of the water because it's heavy. But here's the thing, water's density would be in between those two. Anything with a density greater than water sinks. Anything with a density less than water floats. So if you are able to take a pure, um, a, a bag of water that had this exact shape, a sphere of water the size of a basketball, it would be heavier than a sphere of wood the size of a basketball. The wood would be lighter than the water for the same amount. Does that make sense? Anything with a density less than water floats. Anything with a density greater than water sinks. Well, not only do solids have density, so do liquids and so do gases. This is why oil floats on water, because its density is less. Okay? What I want you to do is think about this. Is there a relationship between the speed of sound through a medium and its density? What's the density of hydrogen gas compared to water? Which is denser? Well, let's slow down here. Maybe we're not sure about hydrogen gas. What about marble? How heavy is a piece of marble compared to water? Would marble sink? A piece of marble would sink, like a marble statue. Is its velocity greater than the seawater? Yeah. How about air? Does air rise to the top of water? Yeah. And look how dense it, and look at its speed is much slower than the speed of sound in water. Right? This is why it's hard to hear which direction a sound is coming from when you're in the water. Like if you ever get the chance to go scuba diving, sound waves move so fast through water, they basically hit your ears at the same time. And so you're underwater and you can hear a boat, but you can't tell if it's that way or in front of you or behind you. You can't tell. If you're in the air, you can tell though, huh? Because your brain can actually tell the difference between when a sound wave hits your right ear and when it hits your left ear. Your brain can recognize that subtle difference in sound timing. But underwater, it's too fast. You can't tell. How about human tissue? How about lead or steel? Which of those has the fastest sound wave? And do we see that the more dense materials have the faster sound waves? Which three materials do you think are the densest on here? Yeah, I would say steel, marble, and lead, huh? Do they also have the fastest sound waves? Looking at their speeds, they have the fastest sound waves, huh? And our least dense materials like air and hydrogen gas have the slower sound waves, don't they? Okay, with water in the middle. So what did I want you to do? Describe the relationship between the speed of sound and its density. The faster it is, the density. But that's actually backwards. It's because the density causes the speed to increase. Think about this. If the molecules are packed closer together, would it be easier for the sound to vibrate them? If they're spread apart, it would be harder for them to bump into each other, wouldn't it? So does density influence the speed of sound? I think so. So here you could say the higher the density, the what? The velocity of sound. The more dense it is, what do you think? Faster or slower sound? I'm going to let you decide. And use this chart if you need help thinking about it. Which ones are more solid? Those are the denser ones. And then the third bullet. What do you notice there? Look at the chart. At least as far as velocity of sound goes, we can compare it to density. What do we see for human tissue versus seawater? Yeah, so put down your answer. Basically, our cells are almost like little plastic bags full of seawater. Very similar in content, mostly water, but then there's different salts dissolved in our cells, just like there's salts dissolved in the ocean. Next, circle the correct descriptions. As sound travels from a high-speed medium to a lower speed medium, so let's find an example. From a high speed to a lower speed. Here's a good example, from marble to air. As it goes from high speed marble to low speed air, the frequency does what? You circle. Does it increase, decrease, or stay the same? And then the wavelength does what? Does it increase, decrease, or stay the same? So use as your example going from marble to air. High speed to low speed. 3,810, slowing down to 330, going from high speed to low speed. What did the frequency do? What did the wavelength do? Circle the correct answers. And then the same thing for the last one on that page, but now you're going to fill in the blanks instead of circling answers. Right? And your options are going to be increases, decreases, or stays the same for both blanks. But now it's backwards. It's going from low speed to high speed. I would use maybe this one as we go from human tissue at 1,540 to steel 5,960. What happened to the frequency? Did it increase, did it decrease, or did it stay the same? And what happened to the wavelength? Did it increase, decrease, or stay the same?
I don't even know what this happened. Whole page two. I'm trying. Click on one of the boxes.
Yeah, it moved all your answers onto this page, and it should be the previous page. Right? Oh, wait. You lost the whole page.
Yeah.
The page disappeared.
I clicked on one of the boxes.
Why don't you get out of this for a minute and just go to files and come back? Well, you can, posts, out of the posts. Then you come back. Hopefully it'll come back, yeah. Okay, try coming back. All right, we're going to try to finish page 15 today also. So let's move on to page 15. And I'm going to ask you to highlight the important parts as we read through this together. First of all, look at that speed limit sign. I'm sorry, you can go no faster than 299,792,458 meters per second. Sorry, you can't go faster than that. That's the speed limit of the universe. And do you notice that that's pretty close to 300 million? Which is 3 times 10 to the 8th, or 3e8. Did we see that number a lot when we did the light math, right? That's the speed of light through empty space. Now, through other materials, it's a little slower, but light waves can travel almost 300 million miles an hour in empty space, but we don't think anything can go faster than that. We have no evidence that anything can travel faster than light. Okay? And yet it still takes 8 minutes for light to get to us from the sun. And the closest star besides the sun is like 5 light years away. That means it takes the light from that star 5 years to get here. Some stars are even further away than that. For example, there might be a star that is 100 million light years away. That means it takes light from that star 100 million years to get here. Think about that for a minute. When you look at that star, are you seeing it as it is? You're seeing it as it was 100 million years ago. And vice versa. If there was a planet around that star that's 100 million light years away, and there was an advanced civilization on there that had really powerful telescopes, and they looked at the Earth, they wouldn't see you. They'd see the Earth as it was 100 million years ago, which means they would see dinosaurs alive and walking around.
What?
It's crazy, right? The universe is a big place.
They would see dinosaurs?
If they were 100 million light years away and they had the right kind of telescope, yeah.
So it's like seeing into the past.
They're seeing into the past. In fact, we call it look back time. We're looking back in time. And the further away something is, the further back in time we're actually looking. And this is where some of the evidence for the Big Bang comes from. If we look back far enough in time, we can see the origin of the universe. It's crazy, isn't it? Yes, sir. Yeah, that's actually how it works. I don't think there is a telescope that would allow you to see the organisms on a planet. We certainly don't have one. We can just barely make out a planet right now, huh? Let alone what's on it. But if they had something, that's what they would see. On the other hand, check this out. Radio waves travel through space, don't they? TV waves travel through space. And every TV wave that has ever been broadcast is still traveling through space. And one of the very first TV broadcasts was Adolf Hitler, which means a civilization that first receives our radio waves, that's going to be their initial impression of the Earth. Yeah. They spread out. So they're more and more diffuse is what I would say. Yeah. So basically we would see their amplitude going down. But they're still going. There's nothing to stop them. It's just that they're more spread apart. And it would take a more sensitive receiver to pick up the signal. You know how like sometimes you have to move your cell phone around to get a good signal? You're trying to find where the radio wave is right, huh? And that same thing would be happening out there in space. So let's read this together and please highlight the important stuff as we go. The wave equation, velocity equals frequency times lambda, wavelength, applies to both sound and light. If light can pass through a medium, the light waves are slowed down a bit because the light gets scattered by the atoms in the material when the light waves bump into them. The amount by which light slows in a given material is described by something called the index of refraction. And we use the letter N to represent that index. So a material that scatters light a lot has a high N, has a high index of refraction. The index of refraction for light allows us to predict the speed of light through different materials. Oops, that's no good. Since the vacuum of space has no atoms in it, this is where light can reach its maximum speed. This is known as the ultimate speed limit of the universe, since nothing can go faster than light in empty space. Now, this also would mean if we wanted to visit those people that are 100 million light years away, it would take us 100 million years to get there if we traveled at the speed of light. And so we don't think anything can go faster. Now, in some science fiction shows, they've invented technology that goes faster than the speed of light. Like on Star Trek, they call it warp speed. faster than the speed of light. But physicists today don't think that can actually happen. If it could, then we could really explore the universe. If it can't, then we're kind of stuck. And the only way we could explore the universe is if we had like a giant spaceship that had 1,000 people on it that were all families that kept having more babies into the future that would allow that spaceship to continue into the future, and whoever launched would be dead long before it arrived at its destination. Yeah. Right now, with our current understanding of the universe, no, it's not possible to travel at the speed of light, unless you're light. So where did we leave off? Nothing can go faster than light in empty space. This speed is represented by the letter c, since it is a constant value everywhere in the universe. This speed limit sign shows the speed of light in empty space measured in meters per second. If we round this off and change it to scientific notation, we get 3 times 10 to the 8th, or 3e8 meters per second. Are we good with that? The index of refraction of a material, again, this is represented by the letter n, and it's shown in this data table. It's given to you. It is defined by the speed of light in a vacuum divided by the speed of light through the material. In other words, n is the speed of light divided by the speed of light. But it's the speed of light in a vacuum divided by the speed of light in that material. Maybe in air, maybe in water, maybe in glass. Okay? That's how we find the index of refraction. It's been given to you here, but we're going to calculate the speed of light through that substance. To do that, we use algebra, rearrange the equation, and we end up with V equals C over N. In the table below, use the index of refraction to calculate the speed of light through different media. And we're going to use scientific notation here. So first of all, what is the speed of light in a vacuum? What's the number we've been talking about? Speed of light in a vacuum. Well, it is this number, huh? But why don't we round this off and make it simpler? What should we round it to? Instead of 299 million, why don't we make it 300 million? But let's use scientific notation, which is 3e8, or 3 times 10 to the 8th. They both are the same thing, right? So what are we going to do? Well, we're going to take this equation to fill in this table. The velocity is what we're looking for, and it varies with materials. So here, oops, I should have kept that equation. What was it? C divided by N. This is C right here, huh? Yes? So we're going to take 3e8 divided by 1. What do we get? That should be easy. Anytime you divide something by 1, you... What's 5 divided by 1? 5. What's 37 divided by 1? 37. What's 892.634 divided by 1? 892.634, right? Whatever you divide by, you get it back again. So doesn't that mean that this is going to be 3e8? Right? 3 divided by 1 is still 3, with 8 zeros behind it. Next, let's do the first one or the second one together. Please put in your calculator 300 million. You need 3 and then you need 8 zeros. divided by 1.0003 equals, do you get 2,999,10027? We're just going to round that off, and we're going to call it 2.999 E8. Is that okay? So can you see that the speed of light through air is just slightly less than the speed of light through the vacuum of space? Air doesn't slow it down very much. It slows it down a little bit, but not much. What are you going to do for the next one? 300 million. So that's 3 with 8 zeros. Oops, I lost count of how many zeros I put in there. Got to put in the right number of zeros. I like to go 3, 0, 0, 2 zeros, then 0, 0, 0, 3 more, and then 0, 0, 0. That's what I'm doing in my head. 3, 0, 0, 0, 0, 0, 0, 0, 0. Divided by 1.33, huh? Equals 22556, etc. We're going to just round all that off. It's going to be 2.256 E8. Are you with me on how I'm changing it to a scientific notation there at the end? I moved the decimal over 8 places, and I just ignored a bunch of the digits. Okay, so I would like you to continue filling in this chart. If you're doing it right, you're going to see the number gets smaller and smaller every time. It should still be E8 at the very end. Each number should end up smaller and smaller. And we're keeping 3 decimal places. And we've got about, what, 5 minutes left maybe? What I would like you to do with the remaining time is finish this page. Just answer the questions after filling in the table. Okay? So your goal when I see you again, wait, I don't see you again until next week, is that right? Okay, so your goal between now and then is to have everything in this project done up to the end of this page 15. You don't have to go past 15, but everything before that should be already done, right? So if you fell behind on something, homework is real, okay? I know you might not believe in it, but it's a real thing. Yeah, but you don't want you to have to redo everything. I have an idea. Did everyone else stay the same? The old stuff, is everything good back here? Thank you for that. Yeah, that's the guys was there. Maybe what we should try doing is, what you guys leave for your table of contents. My whole list. I'm not going to rename this. So we need this page. How we look at the country and put it in a database, upload it, upload the original again. Call that my project part 2. And I'll know to check the first half on this page, the second half on that page. Is that one page somewhere? We don't know how to get back. So it might be best to just do that. Can I explain that?
Yeah, because it's all fruit.
Yeah, it's so nice though. It's so nice. I went to this other practice on it was grass.
Anybody at home have any questions for me about what you've done, about how to do it, about what I want you to do before I see you again over the weekend? Okay, everything should be done. Pages 1 through 15 should all be finished before I see you again on, when do I see you? Tuesday? I think Tuesday, yeah. Have pages 1 through 15 done, okay? You guys can check out now. Thanks for being here.